welcome. We get started in just a second. We're going to be picking up with chapter 14, which is after obviously chapter 13 in the gases, which we finished last time. And a reminder, as we talked about last time, chapter 14 will be moved to exam 4. So it will no longer be part of exam 3. So again, exam 3, which is scheduled for, I believe, a week from Wednesday, will be just through chapter 13. And again, we'll get started in just a second with chapter 14 as we finish chapter 13 during lab, if I'm not mistaken, last week. Okay, so we'll get started. So again, just for everybody that just maybe came in, we are starting chapter 14 today, which should be liquids, basically. I'm not going to do too much on solids. Again, 14 was originally scheduled for exam 3, which is next week, but it has been moved from exam 3 to exam 4. And so exam 4 will be chapters 14, 15, and 16, if I'm not mistaken. And this previous exam, which is coming up next week, we'll go through chapter 13, which was the last chapter, the gas chapter that we talked about last time. All right. Again, if you have questions throughout, make sure you type them and ask them in the chat box, even if we happen to move past where we're at, where your question may be from. I will go back, obviously, and answer your questions and stuff like that. So if you go on the Canvas page, chapter 14 has been moved into exam 4's lecture notes, along with chapter 15, which is up there as well, which we may get into today during lecture. And really, that leaves us, we got 14, 15, 16, and 17. That's it, 4 chapters to go. Then we're all out of chapters for this semester. All right. So again, what we're talking about today will be officially on exam 4. So we're going to talk about liquids and solids in this chapter. Really, honestly, we're going to talk more with solids and sort of, more with liquids than solids, and a little bit about some different properties. The first thing we're going to talk about is water and sort of the different phases of water that we see. Water obviously is colorless, tasteless. Its freezing point's at 0 degrees Celsius, and it vaporizes or goes into the gas phase when we get to 100 degrees Celsius, which is its normal boiling point. And we have liquid water between 0 degrees Celsius and 100 degrees Celsius. It's really not until we get a little bit below 0 degrees Celsius that we do have sort of ice, until we get a little bit above 0 degrees Celsius that we have liquid water. And the same idea there when we're at 100 degrees Celsius, it's not really until we get a little bit above 100 degrees Celsius that we truly have just steam or gas. We have a little bit below 100 degrees Celsius. That's really where we will get sort of liquid occurs. So we'll see a much better drawn curve, I think, a little bit later on, but we'll put it up here maybe. So if we just kind of look at it coming this way, and if this is ice down here, say this is liquid water, and this would be steam, or obviously the gas phase of water. This would be 0 degrees Celsius. This would be 100 degrees Celsius. And when we get to these parts here where we're transitioning, this would be its normal freezing point. Also its melting point, right? As we go backwards, right? If we go from liquid to ice, that's freezing. Going from ice to liquid, that's melting. Same thing up here. This is where those transitions occur between liquid and gas, right? That's where evaporation occurs as we go from liquid to gas, or steam in this case, and condensation, right? If we were going the opposite way, going from gas back to liquid. And those processes, both freezing and melting, they occur at the same temperature. And for water, that is 0 degrees Celsius. And same thing with evaporation and condensation. Also occurs at the same temperature. And again, for water, that temperature is 100 degrees Celsius. So at exactly those temperatures, say 0 degrees Celsius, for example, for water, what we essentially have is sort of ice crystals. So you got basically in equilibrium, the liquid phase and the solid phase happening exactly at the same time. And that would be exactly at 0 degrees. And we would see, again, some solids, some liquid. But as soon as you get a little bit above 0 degrees, that's when you should truly transition to all liquid water. And if you get a little bit below 0 degrees, it'll all transition to sort of solid. And the same thing happens at that 100 degrees Celsius. Again, exactly at 100 degrees Celsius, you have an equilibrium, basically the gas form of water and the liquid form happening at the same time. And again, if you get a little bit above, that's when you'll fully transition to gas, or a little below 100 degrees when you'll fully transition to liquid. So, yeah, so what it says there is, I got some boxes in my way. Let me take a look here. What it means, Grace, is what it says there is you have liquid water between 0 and it's actually 100 degrees Celsius. Yeah. So in between 0 and 100 degrees Celsius, which was be on this curve right here, kind of the greenish area. I'm really badly drawing that. But really between that 0 and 100 degrees, that's when you have liquid water. When you get to exactly 100 degrees or exactly 0 degrees, you have each of those phases in equilibrium with each other. And we'll talk a little bit more about it in just a second. But again, at 100 degrees, you basically have exactly some gas there. You have some liquid happening exactly at 100 degrees. And that's why when we look at these lines here and on the graph like this, and we'll see a much better picture later. But when we look at these lines on the graph, that's why these lines here at exactly 100 degrees, and again, envision a nice straight line there. These lines really plateau out and they become flat exactly at 0 degrees and exactly at 100 degrees. And that basically means that, exactly at that temperature, nothing's really changing in terms of the phase, but you do have both of those phases together at the same time. So what really determines sort of which way you go at those temperatures is energy, right? So energy is really the thing that determines, what happens at those temperatures. So if you do sort of an endothermic process where you put heat and energy in, you will continue down sort of this path going from solid to liquid. And same thing would happen higher up there. If you do an endothermic process, you will continue down the path of going from liquid to gas, yeah, at the other transition. And vice versa, if you do an exothermic process where you remove heat and energy, you will do the process where you go from liquid back to solid at 0 degrees Celsius. And you will go from gas back to liquid at 100 degrees Celsius. So again, at those temperatures, depending on what you're doing with energy, will basically determine sort of what is happening in terms of those phases and stuff. Now, when we talk about water, water is a polar solvent, and it's polar because basically overall it has unequal sharing of electrons, and there's a positive side to water, which is the hydrogen side, and there's a negative side to water, which is the oxygen side. And water has some unusual sort of properties. One very common unusual property is its density. So water is one of the few sort of substances where its density in the liquid phase is actually more than its density in the solid phase. And that is why when we, put something like ice cubes into our beverage, our ice cubes, right, will typically float on top of, say, the liquid part. And that is, again, because ice, which is the solid version of water, is actually less dense than the liquid version of water, which is a very unusual sort of property for substances. So usually substances, basically the other effect occurs when they're in the solid phase. They're usually much more dense than when they're in the liquid phase. And this has a lot to do with what we're going to talk about here as well in this chapter, which is how water molecules, when they come together, again, the oxygen part being more negative, the hydrogen part being more positive because it's a polar molecule. When they come together, a bunch of water molecules, they will be attracted to each other by that positive negative attraction that occurs between different water molecules. And what ends up happening is when all these water molecules basically come together in the solid phase, it creates these really open area between all the water molecules, and it creates a larger volume when they come together in the solid phase. And if you remember, density is mass divided by volume. So if we create a larger volume, that means that our density should be smaller. So sort of an unusual property of ice is how these water molecules come together. They come together, as we'll talk about in just a second, through what is known as hydrogen bonding. And what that does is it just creates a lot of open space between these different water molecules. And that has a big effect on the density. And that's why what we see is this unusual sort of property of water, that it actually is less dense in the solid phase than it is in the liquid phase. Any questions on that there? Okay. Now, when we do transfer from one state to the next, come back, there you go. It does require a certain amount of energy to do that. And there's really two types of forces that hold basically either a molecule together or molecules together with each other. And we're going to talk a little bit more about some of these forces in this chapter. But the first type of force is the bonding force that holds together a single molecule. So basically all the atoms within just one single molecule, that force that holds it together is what's known as an intramolecular force. So for example, if we take just one water molecule by itself, the attractive force that holds together this bond here between this oxygen and hydrogen, and this bond here between this oxygen and hydrogen, this is what is known as intramolecular forces. Intra means within the molecule itself. These are things like ionic bonding, which is not the case above. These are things like covalent bonding, right, where we're sharing electrons. These are intramolecular forces, and they're these strong forces that hold each individual sort of molecule or substance together. Now, when we talk about how a bunch of molecules come together, like I kind of drew on the previous slide here, if we take one water molecule and another water molecule, they will be attracted to each other through that opposites attract that we'll talk about. These forces here that is between different molecules are what are known as intermolecular forces. And the intermolecular forces are the forces that hold one entire molecule, that whole molecule, together with another whole molecule. So it's the forces that hold all those together. So when we think about which one is sort of stronger, the strongest one in terms of between intramolecular forces and intermolecular forces, this one is much stronger. So intramolecular forces are very, very much stronger than intramolecular forces. And we know that by just a practical example of something that you probably have done before, which is like when you boil some water to make some pasta. When you boil water to make pasta, what you essentially get is H2O in the gas form, which is known as steam, right? What you don't get when you boil pasta is you don't get hydrogen gas and oxygen gas, right? Which would not be very good as you're trying to make your dinner or lunch, whatever it may be. And because we see this, we know that the intermolecular force must be weaker. And that's because as you go to heat it, water, for example, in a pot, the first force that breaks is the force between the different water molecules. So these guys break first, right? And what you end up getting is that water that's in the steam version of it. If the opposite was true, and actually the intramolecular force was weaker, what you would see is instead of the bonds between one water molecule and another break, what you would see is these bonds break over here, which again would make hydrogen gas and oxygen gas, which does not happen. And that would be bad. Basically, all the molecules would fall apart. And basically, you'd have alphabet soup. So all the hydrogen would fall off, all the oxygens would fall off. And again, that does not happen when you heat something like water. So intermolecular forces, and we're going to talk about different types of intermolecular forces a little bit later on in this chapter. But intermolecular forces are weaker than any intramolecular force. And again, intramolecular forces is things like electrostatic attraction, which is the positive and negative attraction that we see in ionic bonding. That's actually an extremely strong intramolecular force. Things like covalent bonding is also an intramolecular force. Things, as we'll talk about a little bit later on in this chapter, things like hydrogen bonding, dispersion forces, dipole-dipole, these are intermolecular forces, and we're going to go through each of those in this chapter as well. Now, when we're talking about a substance sort of changing from one state to the next, there is a certain amount of energy required to do that. And what we see on this screen here is specifically for water. But what we see on the screen was something known as the molar heat of fusion. This is sometimes abbreviated as a delta H of fusion. Delta H is what is known as enthalpy. En. And the delta means basically the change in enthalpy. Enthalpy, it can be thought of as basically the heat for a chemical reaction. And much like when we talked about Q, if you remember, we did heat. If you have a delta H value that is negative, what that implies is this process is a exothermic process, which heat and energy is released. If you have a delta H that is positive, it implies that this is a endothermic process, and heat and energy is absorbed. So delta H is kind of useful in terms of the sign, negative or positive, because it allows you to figure out whether or not overall is energy being added to a system, is energy being released from a system. And the molar heat of fusion is specific for this transition going from solid to liquid, or vice versa, going from liquid back to solid, which for water occurs at 0 degrees Celsius. Again, that number would be different for different substances, but for water, it occurs at 0 degrees Celsius. And it is specifically just to do that transition at 0 degrees Celsius, for example, for water, not going up or down. And if you remember my really bad drawing where we had that flat line at 0 degrees Celsius, that is, say, ice, and that is liquid water. Exactly at 0 degrees Celsius, not going up in temperature, not changing the temperature, but exactly at 0 degrees Celsius for water. There is a certain amount of energy that's required basically just to do that transition, to simply take water from ice, which is the solid version at 0 degrees, and move it to liquid water still at 0 degrees. So nothing's happening in terms of the temperature, nothing is changing in terms of the temperature. And that is what is known as a delta H of fusion. For water, that is 6.02 kilojoules per mole. That's approximately 333 joules per gram. I'm not sure. I didn't see any glitch. Hopefully everybody could hear me okay. Yeah, everything going on. Might just be a connection. Sometimes, it's internet, so sometimes it glitches for a second, but hopefully everybody could hear. I think still, yeah. It was good. All right. So 333 joules per gram is another way that the heat of fusion is sometimes referred to. So this is the delta H of fusion, again, specifically for water. Okay. Yeah, okay, perfect. Sounds good. Thank you for letting me know. So delta H of fusion is 333, again, for water. Now, there's also this transition, which is known as the delta H of vaporization. And the delta H of vaporization is the energy required to do the conversion between liquid and gas. So this happens at going from liquid to gas and backwards, gas to liquid. And for water specifically, again, that occurs at 100 degrees Celsius. And the delta H of vaporization is the exact sort of definition, the exact same definition as the delta H of fusion, in the sense that it is the energy required to take something like liquid water at 100 degrees Celsius and transform it into gas at 100 degrees Celsius. Again, no change in temperature. It again is that flat sort of area of the curve that we saw earlier. This was steam, and this was liquid water, and this was 100 degrees Celsius. It is right there at that flat point between those two phases where this occurs. And again, not changing the temperature, but it takes a certain amount of energy to do that. And that's about 40.6 kilojoules per mole, again, specific for water, roughly that translates to, give or take, 2260 joules per gram, if you roughly kind of do the conversion factor there. And again, that's the energy required to go from one phase to the next. Any questions on that? So molar heat of fusion, or delta H of fusion, is the energy to take a substance from solid to liquid, or go backwards, liquid to solid. Delta H of vaporization is the energy required to go from liquid to gas, and vice versa, go from gas to liquid. And this occurs at the normal freezing points and boiling points for a substance. And again, usually a lot of times we focus in on water, which is the numbers that you see here on the screen, and the 0 degrees Celsius and the 100 degrees Celsius. Again, if you're dealing with something that is not water, they will have different numbers for the heat of fusion or the heat of vaporization, and they will also have different melting and boiling points as well. So keep that in mind in case you come across a question that is sort of like this but not dealing with water. You will have some different numbers to use, and my guess is they would probably be provided for you either in the table or in the question and stuff like that. Any questions on that there? Okay, so here's that much prettier picture of that cooling and heating curve. And in terms of the heating, as we go basically from ice, which is our solid, to here, which is obviously our liquid water, to steam, which is obviously our gas. So as we go from solid to liquid to gas, that is heating. That is all endothermic processes, which means in order to do that, you need to put heat and energy in. And again, if we take an ice cube, it needs to absorb heat and energy. When it does, it will melt to liquid water. If we take liquid water, put it on the stove and put some fire underneath it, it will start to boil and then obviously create steam, right? And obviously going the opposite way, if we have a lot of steam and we want liquid water, remember steam is really gas molecules, right? So they are flying around in all directions, which means we need to remove heat and energy from them. When they do, they no longer have enough energy to basically escape each other, and they'll start to clump a little bit. And once they start to clump, they will go into the liquid phase. And then if they take more energy out, they will get closer together and go into the solid phase. And that process going backwards is an exothermic process heading in the cooling direction. Now, when we talk about heat and energy, and if you remember when we talked about Q, which is heat, right? When Q is a negative value, right, that is a exothermic process. And when Q is a positive value, that's a endothermic process when we talked about specific heat, right? And again, the same thing for our heat of fusion and heat of vaporization. So when we look over here, exactly at 0 degrees, that is where we use our delta H of fusion. And again, as we go from solid to liquid, that's an endothermic process, which means that delta H would be a positive number. And if we're doing the opposite transition, going from liquid back to solid, the delta H of fusion will be a negative number. And again, that is the number, I'll just use the 333 joules per gram. So going in this direction from solid to liquid, it would be positive 333 joules per gram. Going back in the opposite direction, it would still be 333 joules per gram. But the only difference here is the negative version of it. And the same thing happens up here. This is where we use our delta H of vaporization. And this is where we are going from either liquid to gas our backwards gas back to liquid. So if we're going from liquid to gas, that again is endothermic. So the delta H of vaporization will be a positive value, and going backwards from gas to liquid, that is an exothermic. Delta H of vaporization will be a negative number in this case. Again, the number will be the same. So again, that is the like 2260 number, and that is specific for water. So it would be positive 2260 heading in this direction. It would just be negative 2260 headed in this direction, going from gas to liquid. Any questions on what to use that? There's also something known as sublimation, as we talked about, right? Sublimation is when we go directly from solid to gas, skipping liquid. And usually for a substance, if you want to figure out what is sometimes referred to as a delta H of sublimation, you basically could just add up the delta H of fusion plus the delta H of vaporization, because that will essentially take you from solid all the way up to gas again in that process. We really won't come across too much of sublimation or delta H of sublimation, but vaporization and fusion are ones that we come across a lot. Question on that. We also see that when you look at the difference between delta H of vaporization and a delta H of fusion, the delta H of vaporization is much, much bigger in terms of its value. It is 2200 joules versus 333. It's a bad math, but it's something like 7 times greater amount of energy is needed to go from liquid to gas than is needed to go from solid to liquid, as you can see by the smaller dots over here, a smaller line where it plateaus versus this longer line up here, up on the conversion between liquid to gas. And that's because when we are going from in the case of fusion, going from solid to liquid, remember in the solid phase, everybody is very close to each other. In the liquid phase, everybody's still relatively close to each other, a little bit more room for movement. But it's not until we go from the liquid phase to the gas phase that we go from everybody sort of near each other in the liquid phase to in the gas phase, everybody has 100% broken apart from one another, and they're flying around free from each other. And that takes obviously a lot more energy to do that than it would obviously going from solid to liquid, where everybody's still relatively close to one another. Questions on that? Now, where we typically will use, and again, if you do have questions, feel free to type it. I will definitely get to them. Where we use the delta H of fusion and the delta H of vaporization is we actually will oftentimes use it in terms of a calculation with something that we've seen earlier in a previous chapter, and that is our good friend specific heat. And if you remember, our specific heat equation is Q is equal to ms delta T, where Q is heat, right? M is mass. S is the specific heat capacity. And remember, for liquid water, in the liquid phase, that was our 4.184 number that we use. And delta T is our change in temperature, right? Our change in temp, which was in degrees Celsius. So we oftentimes will use specific heat in a calculation along with our delta H of fusion and our delta H of vaporization. So our delta H of fusion and vaporization is used for only changing phases. So when we have delta H of fusion and we want to use it, it is specifically only for going from solid to liquid or backwards at 0 degrees Celsius for water. Again, no change in temperature. While our delta H of vaporization is the same deal, going from liquid to gas or backwards. And for water, again, specifically at 100 degrees Celsius, no change in temperature. So these guys do not change temperature and stay. They don't change temperature, but they do change phases. So in a calculation, whenever you see yourself not changing the temperature of a substance, but changing its phase, like it goes from solid to liquid, it goes from liquid to gas, that is where you should use delta H of fusion or vaporization in a calculation. And that is different than specific heat that we used earlier on. In specific heat, that Q equals ms delta T, that is used when we actually do change the temperature, but the phase remains the same. So if we wanted to figure out how much heat was associated with changing liquid water from 5 degrees to 7 degrees Celsius, 70 degrees Celsius, we would want to use specific heat, the Q equals ms delta T. If we want to figure out how much energy is needed to take liquid water at 100 degrees to steam at 100 degrees, we would want to use the delta H of vaporization. Any questions on that there? So sometimes it's usually very helpful when you're doing these type of calculations is to kind of draw a little graph like what we see on the screen. And anywhere where you draw the graph on the screen and it goes kind of upwards, it doesn't plateau, that is where you should use Q equals ms delta T. So for example, Q equals ms delta T should be used for the calculation anywhere along here where it's going up. Also anywhere along here where it's going upwards, you should use Q equals ms delta T. And then if I move my box out of the way over here, at this area over here on this curve, you should use your Q equals ms delta T. These are all places where we change the temperature, but we do not change the phase. So anywhere in that area, those guys remain the same phase throughout, but the temperature changes. And that is where you should use your specific heat equation. And anywhere where I have in pink there, the delta H of fusion, where you're keeping the temperature the same, but transitioning to a different phase, that's where delta H of fusion or vaporization should come into play. And if you wanted the total amount of energy to do that entire process, for example, you basically just add up each of these steps in terms of energy, and that'll give you the total amount of energy to do that. Couple other things that you do want to think about is if you are down in this area where our ice is, and we're going to use this equation here. When we use the specific heat for water, water is in the form of ice at that point, which is the solid state. So the specific heat capacity for water that is solid is actually not the 4.184 number that we're very much used to. It is something like 2.03 joules per gram per degree Celsius. And same thing up here, if we were in this area where we use the Q equals ms delta T, the specific heat for water, for example, in the gas phase is also a different number. It's something like 2.01 joules per gram per degree Celsius. So the specific heat capacities for substances do change depending on the sort of phase that you're in. So liquid water is the one we traditionally sort of think about, but it's not always the value that you'll use, especially if you're not using liquid water, but you're using water in the gas phase. You'd want to use 2.01. If you're using water in the ice phase, which is the solid phase, you'd want to use 2.03. Any questions on that there? All right, so why don't we try one just to kind of see how this calculation would take place. And I'm just going to make it up here and I'll do it with you. So let's say we want to know how much energy in joules is needed to take ice at minus 2.5 degrees Celsius to steam at 105 degrees Celsius. We'll do 125 grams of ice at minus 2.5 degrees Celsius to steam at 105 degrees Celsius. So joules, and maybe we'll do kilojoules. All right, so why don't you give that a try? Take a few minutes here, 5 minutes or so, to kind of work through that. Then we'll go through it so you can kind of see how this calculation works. Let me give you some information that will probably be helpful. Delta H of fusion for water, you could use 333 joules per gram. Delta H of vaporization for water is 2260 joules per gram. Specific heat of liquid water is 4.184 joules per gram per degree Celsius. Specific heat of solid water is whatever, they're both basically 2.03. And the specific heat of gas or steam is 2.01 joules per gram per degree Celsius. All right, give that a go. Then I will as well, because I just made it up. So take about 5 minutes or so. And we want the total amount of energy. So we want basically the total amount of energy, right? Total. All right, so take a few minutes there, 5 minutes, and I'll be quiet. If you have questions, feel free to type them. I'll type back to you during this process, and then we'll go over this one in just a second. So the S next to the water signifies as water in the solid phase, so like ice, basically. And G next to the water would signify it's in the gas phase, which means something like steam, that you get when you boil water. And then L obviously is liquid water, basically, like it comes out of the tap. Okay, so let's take a look at this and kind of see how we're doing here. Grab a calculator, might need one of those. So this is one where we're trying to figure out energy as we're transitioning phases. So sometimes it's really good to kind of make a little graph like we saw previously, just to kind of keep track of where we're at sort of in this process. And again here, not drawn great, but we're going to call this 0 degrees Celsius, which is our normal freezing point. Very badly drawn one there. This will be 100 degrees Celsius coming this way. So when we think about where we're starting, we basically, again, this is our ice, right? This is our liquid water. And this is our gas water, right? Or steam basically up here. Really our solid. So in this process, we want to figure out how much energy is required basically to take our ice cube all the way down from, say, let's just call it down here, starting here to all the way up to here in those processes. So we want to kind of think about it in sort of steps. So we are starting with minus 2.5 degrees Celsius. And we have 125 grams of ice, which is basically the amount of water we'll have throughout the entire process, as nothing should be changing. So the first thing that we want to do or need to do is essentially take our ice that is at minus 2.5, and we need to take it all the way up here to 0 degrees Celsius. And I'm just going to call this step number 1. Now, in step number 1, we're going from minus 2.5 degrees Celsius to 0 degrees Celsius. That whole process that I just made purple, that whole process is where the water is still in the solid phase, but we are changing the temperatures. So for the first step, you might have to turn up your volume maybe, Zach. I think we can still hear, yeah. So, but obviously if he can't hear, he probably can't hear that. So let me just send him. Yeah, inside. So we are going to use our specific heat equation, which is our Q equals ms delta T for that first process. And our Q would equal, in this case, our mass, which is 100. It is 125 grams. Our specific heat capacity in this case is for ice. So that is what this S is. So I might have misunderstood Grace's earlier question, but this S here is specific heat capacity. So that's specific heat. And since it's in the solid phase, we don't want to use the 4.184 version. We do want to use the one for ice, which would be 2.03 joules per gram per degree Celsius. I know it's technology. It's supposed to make things so much easier. Sometimes it doesn't. Our final temperature is 0 minus our initial temperature, which is minus 2.5 degrees Celsius. And that's going to be important because that will switch our negatives right into a positive. And for that very first step is going to require, we'll call it 634.4 joules of energy. It is positive number, which we would expect since we're putting energy in to do that. Any questions on that first step? So that first step gets us to 0 degrees Celsius with our ice. The problem is it's still in the form of ice at this point. So we then need to do the next step along the way, which would be to take our ice at 0 degrees Celsius, not change the temperature, and take us to liquid water at 0 degrees Celsius. So this is going to allow us to do the phase change, and that would be the second spot that we would do. And in this process, as we talked about, when we do not change the temperature, but we do change the phase, that is where we want to use the delta H of fusions for water in this case, especially when you're going from solid to liquid or backwards, right? So that's what the heat of fusion is for. So step number 2 is we haven't spilled anything, so we still have 125 grams of water or ice at this point. Because we are going from solid to liquid, that's an endothermic process. So this 333 joules per gram will be a positive number. The grams will cancel each other out. Again, this is our delta H of fusion for water. And we get this number of 125 times 333. That looks like 41,625 joules for this step in the process. Any questions up until there? At this point, we are now sitting with liquid water at 0 degrees Celsius, which is close to where we want to get. Are you talking about the negative sign up here, Grace, with the specific heat? Yeah, so remember that when you do, let me write up here, when we do our change in temperature, it's our final temperature, right? Minus our initial temperature. So our initial temperature in this case was actually minus 2.5 degrees Celsius where we started. Our final temperature was 0 degrees Celsius. So the negative and negative makes it a positive in that case. So that's why, again, just like we talked about with specific heat capacity, you want to make sure that you always do final temperature minus initial temperature, because that will get you the correct sign when it's all said and done. Other questions on that? Okay. So now we're sitting with liquid water at 0 degrees Celsius. The next process that would occur is we need to take that liquid water at 0 degrees Celsius and we need to take it all the way up to liquid water at 100 degrees Celsius. So this again is a place where we're going vertical on this graph. We are changing the temperature, but all the way through that process in green here is still liquid water. So this again is where we want to use our Q equals ms delta T on this one, which again is the equation where we use for the same phase but change the temperature. We still have 125 grams of that ice we started with. Now, the important part here is actually S. The specific heat capacity at this point is no longer the 2 number because we have now transitioned into liquid water. So this is where we would want to use the specific heat capacity for liquid water, which is that number we're used to, that 4.184 number. And now again, our final temperature is 100. Our initial temperature is 0. So we would have 100 minus 0 degrees Celsius. And if we do this part of the calculation here, we got 125 times 4.184 times 100 gives us 52,300. So that's 52,300 joules. I didn't miss a 0, right? Looks good. At this point, we are now sitting at 100 degrees Celsius, and we are still at liquid water. We eventually want to get to steam. So we do have to do another transition of phase, and we'll go with pink. Why not? So the next process that we'll have to do, I guess I should have marked that first. Hang on. I think it was that green, maybe. So again, this was 3. So the next process is taking that liquid water that's sitting at 100 degrees Celsius and converting it to gas at 100 degrees Celsius. So again, here we would be going at this point, starting here, going this way to here. This would be our fourth step. Again, we are not changing the temperature, but changing the phase. And that is where the heat of vaporization will occur again, because in this case, we're going from liquid to gas, but you could go the other way, but we're doing that transition. So step number 4 here, we're going to do our 125 grams. We're going to use our heat of vaporization, also going to be a positive number here because it's endothermic. The grams will cancel each other out, and we will end up with a big old number there, and it is 28. So 28.2500 joules. So you can see that in comparison between going from gas, liquid to gas to solid to liquid, a much larger amount of energy is required to do that. That's these two guys here. And that takes us now to 100 degrees Celsius. We have steam at 100 degrees Celsius. The problem is we want to go to 105 degrees Celsius. So that means we have one last step to do here. And this last step here, we'll just go with gray, is going to take it from 100 degrees Celsius steam to steam at 105 degrees Celsius. 5 degrees Celsius. And that would be our last step here. And again, we are changing temperature, but it remains steam all the way through. So we're going back to our Q equals ms delta T. We're going to use our same mass of 125 grams. Our specific heat at this point has changed as well because we're now in the gas phase. And that means we want to use the specific heat here for our gas. And that is 2.01 joules per gram degrees Celsius. Our final temperature is 105 degrees Celsius minus our initial, which is 100. A little bit of room there, squeeze it in. And we get 105 minus 100, and we will end up with, in this case, 1256.3. So 1256.3 joules for that process. Any questions up to there? So again, sometimes drawing a little kind of chart like I did on the left will allow you not to miss sort of transitions that could occur. This is not the answer, obviously. The answer was how much total energy is needed. So to figure out the total energy, we essentially just add up each of the steps. So we're just going to add up each of the steps to get to our total energy. And in that case, our total energy is basically all the steps together. So step 1 plus step 2 plus step 3 plus step 4 plus step 5. I'm not going to rewrite each of the numbers, but I'm just going to take each of those steps and hopefully not miss any. 634.4 was step 1. 41625 was step 2. 52300 step 3. 282500 step 4. And 1256.3. Oops, come back. Was step 5. That gives you a grand total when it's all said and done of 378 315.7 joules. And if we convert it into kilojoules, divide by 1,000, it is roughly 378 kilojoules of energy is needed to do that. Any questions on any of those steps along the way? I divided by 1,000 at the end because to take it from, this looks like a really bad joule here, but the units are joules. So to go from joules to kilojoules, there's 1,000 joules in a kilojoule. So if we take our joules and divide by 1,000 joules per kilojoule, joules will cancel, and that'll get you to your kilojoules in that case. And kilojoules is sort of a very common unit of energy. As you can see, if we left in joules, you get kind of a big number. So sometimes people oftentimes give it in kilojoules a lot of times. Now, this entire process, as we would imagine, since we started with solid and ended with gas, it was all endothermic, so putting energy in to do so, and all these numbers would be positive. So the significant figures, I just went off of the 125 as it had 3 sig figs. We did have the temperature, which was minus 2.5. But remember, when you're doing temperature conversions, it may not be perfect. You could go to 2 if you wanted to. Technically, in this spot here, when we use that number, we would probably go to 1 decimal place, which would be 2 significant figures. With, again, if we really significantly rounded, that guy would be 2 significant figures. So you might have went to a whole number when it's all said and done when you added it up anyway. So 3 sig figs off of the 125 is really why I went with that. But I can see maybe how you got to 2. But as you followed through the whole calculation, you probably would have ended up with whole numbers at the very end spot here. I'm pointing to my screen like you can see that. When you added up this part at the very end, we did addition, you probably would have had mostly at least one whole number from that first one, which probably would have made all your answer come to a whole number at the end anyways. So you probably would have rounded to a whole number. Other questions on that? So again, this is all endothermic. Now, if I had this exact same problem, but we started at 105 degrees Celsius for steam and went in the opposite direction, the only thing that would be different is the signs. So if we ended up going in the opposite direction, if we started up here and we went down, the only difference is the end result would be minus 378 kilojoules as the total energy. The number would be the same, the sign would be different. That is because as we would go down this way from step number 5, at step number 5, if we went in the other direction, these two would switch places, which would give you a negative number. And if we did step 4, if we were going the opposite direction, this guy would become a negative number. We did step 3, these guys would switch places and become a negative number. This guy would be a negative number if we were going in the opposite direction. And again, these two guys would switch places, which would give you a negative number. So it would be pretty much the same calculation if you were going in the reverse direction. The only difference is you would end up with negative values for each of those steps, which would also make sense because it should be exothermic as you're heading out that way. Any questions on how to do this type of calculation? So again, this ties into the specific heat equation that we used earlier on in the semester, and you could use your heat of fusion and your heat of vaporization as you do the specific transitions from the different phases. Any questions on any of this calculation here? Okay, so The next thing we're going to talk about is intermolecular forces, and there's a few different types of intermolecular forces, but as a reminder of what we saw earlier, intermolecular forces are those forces that hold one entire molecule together with another entire molecule. And that is the type of force that, again, is weaker than those intramolecular forces that we talked about at the beginning. So there are a few different types of intermolecular forces that we're going to talk about. So let's talk about sort of these different types of them. So in terms of intermolecular forces, they are basically, all of these forces basically use a very common way of being attracted to each other. It is the positive and negative charge that is there. It is that electrostatic attraction that really holds one particular molecule together with another. Now, the first type of intermolecular force, and there's a slide later on that kind of lists all these, and we'll see it in just a sec, is what is known as a dipole-dipole interaction. Our dipole-dipole force. And you might remember dipole from bonding. When we talk about dipoles, those were like those little arrows that we drew when we did bonding. And if a molecule is polar, it will have what is known as a dipole moment, which is basically a fancy way of saying there is a negative side to the molecule and a positive side to that molecule. So there's a side, because of unequal sharing of electrons, that's more positive, and there's a side that's more negative. And what that essentially does is, because of that, you essentially will have two molecules that are polar, that has a positive side and a negative side. And another polar molecule that has a positive side and a negative side. And because these guys have a positive side and a negative side, that gives these molecules a way to interact with each other. The positive side of one molecule will be attracted to the negative side of the other, and that is their classic dipole-dipole interaction. This is essentially the force that is used when a polar molecule comes together with another polar molecule. So this is really the strong force that occurs when two polar molecules come together. Now, there is a certain type of dipole-dipole interaction that is known as hydrogen bonding. And hydrogen bonding, as the name implies, is a bond between hydrogen and an electronegative atom. Like nitrogen, oxygen, and fluorine. And if you look on the periodic table, those guys are right there in the same row, right next to each other: nitrogen, oxygen, and fluorine. So water is an example of that. When we look at water, water is a polar molecule, which means the oxygen side is more negative, the hydrogen side is more positive. And this is a bond between hydrogen and oxygen. And it is attracted to another water molecule, for example, the same way, because on this guy, this hydrogen is more positive, this guy is more negative. So the negative in one will be attracted to the positive in the next. And this right here is what is known as hydrogen bonding. Now, if you look at something like this, for example, CH4, which is methane, You may say to yourself, this guy probably should be able to hydrogen bond. He's got like a ton of hydrogens. But when you look at the carbon hydrogen bond, that is a nonpolar bond. Also, when we look at this hydrogen, it is not attached to nitrogen, oxygen, or fluorine. So although this has a ton of hydrogens, it cannot hydrogen bond because it does not have a bond between hydrogen and nitrogen, oxygen, fluorine like we see over here. Because there's that bond between nitrogen, oxygen, fluorine, it creates that separation of charge and allows that sort of positive negative attraction to occur. Now, if we look at something like NH3, this NH3 can hydrogen bond. NH3 is trigonal pyramid. If you remember, we see dots on the center atom. Everything on the outside is the same. This is a polar molecule, which by definition means there's a positive side and a negative side. Hydrogen again being positive, negative side being the nitrogen in this case. So, you know, if you had two of these guys, there could be a hydrogen bond between the hydrogen and the nitrogen that's occurring. So just because something has hydrogen, it does not mean it's able to do hydrogen bonding. It does need to be a hydrogen that's attached to a nitrogen, oxygen, fluorine. And that's because these guys over here as well, most electronegative, right? Which means they're going to cause that separation of charge to occur and those electrons being shared unequally. And when we talk about these two in terms of strength, actually hydrogen bonding is a much stronger intermolecular force than the dipole-dipole. So this guy is the strongest. This is the next strongest. And dipole-dipole is typically used for polar molecules that cannot hydrogen bond, while hydrogen bonding is used for polar molecules that can hydrogen bond. Okay. So we're almost to the end. Let's just finish up this last little bit here and then we will get to it. So let's talk about what happens when we do get this guy. This guy is basically what is referred to as dispersion forces. And dispersion forces are really used for nonpolar molecules that interact with other nonpolar molecules. And these are actually the weakest out of all of the intermolecular force. These are temporary sort of interactions. So these are very weak and temporary interactions. So for example, if we had two nonpolar molecules, and a nonpolar molecule, because they're nonpolar, it basically means that they're going to be sharing their electrons equally, and essentially will mean that there's no charge in any of these guys. But electrons are flying around, so if all the electrons decided to sort of head over to our left-hand side of this molecule, what's going to happen is this side will become more positive on the right-hand side, and the left-hand side would become more negative. And now what's going to happen, right, is if it's still next to this nonpolar molecule, This guy normally doesn't have a charge, but it gains a temporary charge. This guy over here. All the positive guys in this molecule, right, are not going to be near those positive guys here. So our positive guys in this guy will then go that way. Our negatively charged guys will head this way. And now the second molecule, which normally does not have a charge, will gain also a temporary charge. So now what you end up with is two guys that normally would not have a charge, any type of separation of charge, but now they have gained these temporary charges. And what's going to happen is they now will have a place where they can interact with each other through that positive and negative attraction. And they're temporary, which means as soon as the electrons in this guy decides, we'll go back the other way, they're going to break apart and new bonds will form, new temporary bonds will form, they'll break apart. And they continuously kind of break apart and make new ones, and break apart and make new ones. And they're very temporary. So that is what something like CH4 would mainly use, is dispersion forces, because again, it's a nonpolar molecule. And the best that it could do is these sort of temporary forces. And again, they would be known as dispersion forces. So in terms of intermolecular forces, which is what we've been talking about here, the strongest is hydrogen bonding. The weakest is dispersion forces. And sort of in the middle is our dipole forces. So again, this is guys that can hydrogen bond and are polar. These are guys that are polar but no hydrogen bonding available. And these are guys that are typically nonpolar molecules. Any questions on any of those there? Okay, so we're going to stop here, I think, today. We're almost through 14, pretty much. We'll just kind of recap the last couple of things out of 14 next time. We will then go into chapter 15. We will be taking a quiz next time. So we'll do the quiz, I think, at during lab time. So we'll do it at 12 o'clock. So at 12 o'clock, you could go and take the quiz. Again, the quiz was on, I believe, balancing equations and stoichiometry. So just like last time, you'll need to, or the exam, you'll need to obviously show some work for the problems that need work associated with it. And then you'll be able to upload it. I haven't decided yet in terms of time, but like your normal time. So, you'll at least get, I would think, 30, 40 minutes, I would think, somewhere in that range. So maybe a couple minutes more because it's online, but you'll probably have about the same amount of time. The exam is a very good question. I wish I had that in front of me. I want to say the exam is next Wednesday, if I'm not mistaken. Whatever it is on the schedule, I think it is. Whatever it is on the schedule, I think is when it should be. And if I'm not mistaken, I think it's next Wednesday, a week from this Wednesday. Yeah. Okay. Yeah. So whatever it is on the schedule should be when it's going to be. And I believe, again, it is a week from Wednesday, which would be whatever date we're at, 22nd. Sounds good. And again, remember, it will cover everything but chapter 14. So again, chapter 14, which is what we're currently talking about, will be moved obviously to exam 4. So again, that should be, if I'm not mistaken, balancing equations. We should have some types of reactions. We should have stoichiometry, moles, and all that kind of stuff, if I'm not mistaken, or stoichiometry. Any other questions on any of that? Okay, so today's lab is, and again, we'll take a little break and I'll start the lab section in case you have questions on either of the labs. I already posted last week, I think experiment 17, I think it is, um, the hydrogen gas one. And in just a second, I'll post the next experiment, which I think is 18. That should be the decomposition one. Both of those will be due tomorrow. Okay, you can turn them in before that, obviously, but the last date you can turn them in will be tomorrow. And again, I'll be there during lab to answer your questions. The quiz is this Wednesday, so 2 days from now, which is 14th, 13th, 14th, 15th. Yeah. So it should be on this Wednesday. Again, balancing equations and stoichiometry, and we'll take it starting probably it'll be available at noon around our lab time. So I'll post the lab that's for today. And again, we'll take a little break and I'll open up the lab session. And again, you can pop in if you have questions or anything like that. And again, I think both of them are due tomorrow, the latest. Any questions on anything like that? Okay. Yeah, so dispersion forces are temporary forces, I think is your question. Yeah, they're the weakest of all the intermolecular forces. They're temporary. They just kind of occur because the electrons shift and creates a temporary charge on that molecule that normally doesn't have a charge on it. And that gives it a way to interact with each other like we see over here. These are temporary charges and temporary forces, basically. And as soon as those electrons shift back, they'll kind of break apart and form new ones. Any other questions on any of this stuff? All right, so it's like 12-ish, so figure maybe about 12:15 or so. I'll start the lab meeting, and again, you can pop in. I need a minute or two, and then I'll click on the experiment for today. So if you go right there, right this second, you won't see it, but about a minute or so, it should be up there for you to see. All right, if there are any questions, we'll end this lecture meeting, and we'll see everybody in about 15 minutes for lab if you have questions. Otherwise, I'll see you Wednesday for the quiz, or lecture after the quiz after lecture.